if we consider a mass on an incline, so this rectangle here represents a mass resting, sliding, whatever, along an incline, and we want to resolve the components of its weight. Okay, people are going to very often, people in this course will very often just quote a formula: mg cosine theta for this component, mg sine theta for this component, even though this is really negative mg cosine theta and this is negative mg sine theta. And then the reaction forces, or the elastic response to this force, the normal force, is going to be equal and opposite, and it will be mg cosine theta if there are no other forces acting. And then the component that you need up the incline to slide this at constant velocity, let's say, in the absence of friction, would be mg sine theta. But those are convenient formulas, but they get misused and people mess up signs, S-I-G-N-S, okay, plus and minus signs. The analysis of the situation there involves constructing triangles, as you well know if you're into if you're in this habit. Involves constructing triangles and then deciding whether everything is positive or negative. That's too many decisions to provide a really reliable analytical process. Okay, theoretically it works just fine, and in practice maybe it works real well if you get used to being very careful about the signs, but I think it's unnecessary. So I'm going to ask that everybody do this analysis in the way I'm going to outline here, and in a way we'll discuss further in the future. Okay, so again, what I'm going to say here is a robust calculation scheme. There's no need to worry about the signs, S-I-G-N-S. But there's a balance on the other side. It's important that you know how to do this with triangles also, if you're going to be an engineer especially. So this is less intuitive. There are no triangles involved in this interpretation. I mean, they're implicit, they're all over the place, but we don't need the triangles to do the calculation here. So here it is. First of all, we put our x and y axes such that the x-axis is along the incline. It's in the direction of the incline. The advantage to that, and the reason that simplifies life immeasurably, is because then we have equilibrium in the y direction. The object stays on the incline, so it has zero velocity in the y direction at all points, meaning it has zero acceleration. And it's zero acceleration that's the condition for equilibrium. So there's zero acceleration in the y direction. This means all the forces in the y direction add up to zero. So that's very important. And people who want to use the cosine and sine of the angle of elevation are well aware of this. And if you aren't at this stage aware of all this, you will be. Okay, so what I want you to understand at this stage is if we have an object on an incline where the incline has angle of elevation theta, that is, the angle between horizontal and the incline is theta. We set up a coordinate system like this, and then we sketch the forces acting on the object. Now, right now, I'm only going to sketch the weight force. We'll worry about the other forces later. But I'm only sketching the weight forces, which is the mg force, mass times acceleration of gravity. We want to find the component of the weight force in the y direction, and we want to find the component of the weight force in the x direction. Now, if we're careful about signs, we can set up SIG-NS, we can set up triangles and do this, but there's a much simpler circular definition of the trigonometric functions that says if you measure the angle from the positive x-axis around to your vector, then you're going to find the x component of your vector by just multiplying the magnitude of your vector by the cosine of this angle. The angle, again, measured counterclockwise from the positive x-axis. And you're going to get the y component by multiplying the magnitude of the weight or the vector, in this case that would be mg, times the sine of that same angle. The sines, SIG and S, take care of themselves. This is a third quadrant angle. If theta is less than 90 degrees, theta looks like, 20 or 30 degrees. So you're going to have an angle of 240, 250 degrees here. That's clearly a third quadrant angle, and you can see from the picture it's in the third quadrant. So this component and this component have to be negative. Well, the cosine of any angle between 180 and 270 degrees is negative, as is the sine of any such angle. So the cosine and the sine take care of the pluses and the minuses, and that's a big advantage in setting things up this way. Another reason I set things up this way is some people are better versed in trigonometry than others. Not everybody in this course has had a course in statics. Not everybody in this course has had a good trigonometry course and understands the trigonometry well enough to do all the trigonometric manipulations that an engineer would do, for example. For physics, this, I think, is sufficient for anything we do in introductory physics. There's something lost by not looking at the triangles, and there are cases where you want to use laws of sines and laws of cosines. We can address those if it's really necessary. But this gives us a framework for dealing with vectors and resolving vectors and adding and subtracting vectors. So this is the scheme I want to use throughout this course, and I want even the engineers who are very good with the triangles and so forth to be aware of this scheme and to become familiar with it. So I'm going to ask everybody to use this scheme. If you want to, in addition, use another scheme, I'm more than happy with that, because you're going to learn even more if you do so.